All right, so we had just defined a conditionally convergent series. And what happens here is that we take a series that has possibly positive and negative terms. We take the absolute value of all those terms, add them all up. And if that new series of positive terms converges, then we say that the original series also converges by the absolute convergence theorem. All right, now if we look at the example right down here at the bottom, basically refers to the initial example that we saw in the warm-up exercise. It is an alternating series. If I take the absolute value, it basically just gets rid of the alternator up at the top and turns it into a p-series, where our p is equal to 2. If our p is equal to 2, this is a convergent p-series. And so the absolute convergence theorem is saying that our series, this one here, converges. Therefore, the original one, the one that without the absolute value, the one that alternates, also converges. It's absolutely convergent. Okay, why does that work? Let's take a look. So back here on this same example we were looking at, let's compare these two things. Which one of these do you think is bigger? Whenever I take the absolute value, it used to have positive and negative terms in it, possibly, but now it only has positive terms, okay? This is the same terms, it's just that some of them are positive and some of them are negative. We're going to be subtracting some of those. So we should be able to tell that the absolute value sum has to be greater than or equal to the one without the absolute value on it, because we're taking some of those terms away. All right, so let's look at this one down here at the bottom as just to illustrate this. So if we were to preserve our alternator here, n minus 1, then that means that the first term is positive, the second one would be negative, and then a positive, and then a negative. Well, since the terms are all the same, I'm actually taking some of that away. The original one would take some of that away, and that sum would be smaller than the one in absolute value. And remember, in another lesson we talked about, if your series is smaller than a convergent series, it must also converge, which is why this absolute convergence theorem actually works. Let's look at an example. Example 2, is the converse of the absolute convergence theorem true? Remember, to make a converse, you switch the if and the then statements. So P implies Q becomes Q implies P. In other words, if your series converges, is it also absolutely convergent? I don't know. Let's take a look at an example. We're going to start by looking at the alternating harmonic series, which in another lesson we definitely said it converged, right? Okay, so now let's take its absolute value. We take its absolute value, and the only thing that happens is the alternator that's right up front here, it goes away. And we're left with 1 over n, and 1 over n, isn't that the divergent harmonic series? All right, well, what this means is that the absolute convergence theorem's converse is not true. Just because your series converges doesn't mean that it is absolutely convergent. And this is an example of one, the alternating harmonic series. It converges, but its absolute value does not converge. In this case, we call it a conditionally convergent series. A conditionally convergent series. What is that? Well, we'll look at this next slide here. A series is called conditionally convergent if it converges, but the absolute value of the terms, that series diverges. Conditionally convergent series. These things are crazy. They're absolutely crazy. And the reason why is because Riemann, you remember Riemann from Riemann sums? Yeah, it's the same dude. He was able to prove that a conditionally convergent series can sum up to any particular number that you want to if you just rearrange the terms differently. This is called the Riemann rearrangement theorem. I wonder if he named it after himself or somebody did that after the fact. Anyway, yeah. So it goes like this. Here's the example that we were just looking at, which is the harmonic series, the alternating harmonic series. And it has been shown that the sum of the harmonic series, the alternating harmonic series, is the natural log of 2. However, let's regroup them. Let's rearrange those things and look what happens. So the first line on this one is basically, whoa, where'd you go? Where'd you go? Wrong direction. The first line in this series is basically the same thing that we have here, right? Okay. So now I'm going to group them. I'm going to group the first two, and then just skip the next one. And then group the next two and skip the 1/8, group the next two, and then so on. Did that because 1 minus a half is positive a half. Bring down the 1/4. 1/3 minus a sixth is positive 1/6, and then bring down the 1/8. 1/5 minus 1/10 is positive 1/10. Bring down the negative 1/12, and so on. You get it. And now notice that all the numbers down here in the bottom are even, which means that we could factor out a half. That's exactly what's happening here. We factor out a half. Half divided by half is 1. Negative a fourth divided by a half is negative a half, and so on. And look at what's in the parentheses here. What's in parentheses here is exactly the sum that we started with, which we said was equal to the natural log of 2. So we've just able to show that the sum of this series is not just the natural log of 2, it's also half of the natural log of 2. What? What this means is that when you have a conditionally convergent series, things like the associative property, things like the commutative property, it didn't hold true anymore. If you rearrange those terms, you would get a completely different sum. That's absolutely crazy. All right, craziness aside, let's take a look at some examples where we're determining whether the series converges or diverges. And then if it does converge, we want to know, is it absolutely or conditionally convergent? Okay. All right, we're going to need some space here, I think. I don't think that's enough space. All right. We also need a blue crayon. Example. Why did I do a sum? Example 3. Yep. Okay, so this first one here, sum from n equals 0 to infinity of negative 1 to the n factorial, n factorial over 2 to the n. All right, notice that this thing is alternating, right? It's an alternating series, and what test are you supposed to perform if you have yourself an alternating series? I think it's the alternating series test. At the second objective, we're going to see that this particular example would be way easier using what is called the ratio test, but we're just going to go with it. All right. So what I want to do is notice that my terms in my sequence, that is n factorial over 2 to the n. Those are positive. Okay, yep. So I'm sticking in 1, I'm sticking in 2, and so on. Well, sticking in 0, whatever. Is it 0? It is 0. Okay. And now the first part of this is that you want to take the limit of your terms and see if they are approaching 0. If you were to stick in infinity, I think you pretty much get infinity over infinity. Infinity factorial over 2 to the infinity. That's infinity over infinity. And problem with this one is that L'Hopital's rule is going to be not very helpful because n factorial, it's not continuous. You're not going to be able to take its derivative. Let's compare it on a calculator. Let's just see which one of those things grows faster. What do you think? So let's open up a new document, pull up a calculator here. Now let's pull up a graph. Yeah, that's what I want. And the first one we're going to do is the factorial, right? Because that's the one that was on the top. And you're going to see it doesn't show anything. And the reason why it doesn't show anything, because it's not continuous, just a whole bunch of dots. Maybe these dots are too small for us to actually see. Let's do another one, which was it x to the n? I don't even remember now. It was 2 to the n. 2 to the n. 2 raised to the, well, it'll be the x power here. Okay. All right, well, we have a function for that one, of course. And since I don't have graphs to compare, what I'm going to look at are the tables, split screen table. All right, so we have the factorials on the left-hand side, and we have the exponentials on the right-hand side. Which one's getting bigger? Which one's getting bigger faster? And you can see that the first term, it's not bigger. The second term, it's not bigger. Third term, nope. But everything after that, the factorial just shoots into outer space, and it gets gargantuan. So what this means is that the top here grows way faster. And since it grows way faster, boop, boop, that means we're going infinity over, like a bigger infinity over a smaller infinity. This thing is going to shoot off to infinity. So let me get rid of all of this and conclude that this thing diverges. That means the alternating test fails, and we need to go back to the nth term test for divergence, like so. I keep the alternator to the nth, n factorial over 2 to the n. Well, this is going to diverge. This thing does not exist, which is not equal to 0. Therefore, this diverges. I'm going to try spelling that word again. Diverge is by the nth term test. Again, we're going to see a different way to do that particular problem whenever we find out what the heck the ratio test is. All right, the second one, we have an alternating series here. We've got from n equals 1 to infinity, -1 to the nth, and the square root of n on the bottom. Okay, so number 2, sum n equals 1 to infinity, -1 to the, was it to the n? Yeah, over square root of n. Okay, it's alternating. Means I need to do the alternating series test, right? So let's check it out. So terms of our sequence would just be 1 over the square root of n, 1 over the square root of n, always positive no matter what, n greater than or equal to 0, no, to 1. There we go. And we need to take the limit as n goes to infinity of our terms. That goes to 0. That's a check mark. And then we also need to check to make sure that our terms are getting smaller, that they're decreasing. I want to check to see the n plus 1th term being less than or equal to the nth term. To do that, set up an inequality. 1 over the square root of n plus 1, is that less than or equal to 1 over the square root of n? It is. The reason why is because the numerators are the same. This denominator is bigger than this denominator. Therefore, this fraction is smaller. Another way to look at that, of course, is just to cross multiply this. Square root of n, is that less than or equal to the square root of n plus 1? Yeah, this guy over here is a little bit bigger. Just a little bit, but big enough. Okay, which means that this thing converges. So, -1 to the n over the square root of n converges by the, that's the alternating series test. We know it converges. All right, the instructions ask us, okay, take that a step further. Is it absolutely convergent? That's what we're going to check next. Absolute convergence? Question mark? So to test that, what you do is you just take the absolute value of your terms. We're going to go the sum, absolute value of -1 to the nth over the square root of n. Well, that will be equal to, it's just going to get rid of the alternator up there, 1 over the square root of n, which, if you prefer, is the same thing as 1 over n to the 1/2. And that's a p-series. Our p is equal to 1/2, which is less than 1, which means this thing diverges. Divergent p-series. Okay, so let's recap. Our original series converged by the alternating series test, and when we took its absolute value, those new terms, the ones that are all positive, it diverges. Therefore, our series is conditionally convergent. Therefore, -1 to the nth over the square root of n is conditionally convergent. Right. And I think that there's one more. Just one more. Look at that thing. All right, hopefully I can remember this. -1 to the n times n plus 1 divided by 2 over 3 to the n. What? All right. So this is number 3. I have negative 1 to the n times n plus 1 over 2 over 3 to the n. I don't know, does it start with 1 or does it start with 0? 1, okay. All right, I got a problem here. And my problem is, what does this do? It's not as obvious as the one that's right up above here that alternates. Does n times n plus 1 divided by 2, does that make this thing alternate? Let's see what happens. So I'm going to examine this exponent here by plugging in numbers. All right, so let's plug in n equals 1. If I stick in 1, I would have, let's see, I'd have 1 on the outside, I'd have 2 on the inside. Divided by 2, I get 1. All right, let's see, I stick in 2. I would have 2 on the outside, 3 on the inside, and then I have 2 divided by 2. These 2's cancel out, and I get 3. So remember, this is the exponent on negative 1. If you raise negative 1 to the first power, it's going to be negative. If you raise negative 1 to the third power, it's still negative. So it doesn't look like it's alternating. Let's try the third one. What is that? That's not n equals 3. I'd have 3 times 4 over 2. That cancels. A 2 gives me 6. I take negative 1, raise it to the 6th power. Now it's positive. All right, so you can see that this is not strictly alternating. It does have some positives. It has some negatives. It's going to switch between them, but not in, by definition, an alternating form. So I can't use the alternating series test. So the best that I can hope for then is possibly, let's take its absolute value and let's see what happens. So let's see if it's absolutely convergent. Because if it's absolutely convergent, then that means that our original one, the problem that they gave us, must also be convergent. So our sum in absolute value, the only thing that's going to happen here is it's going to take this negative 1 to this weird exponent over 3 to the n and turn it into the positive one. I would have 1 over 3 to the n. Let's keep rewriting that. That's the same thing as 1/3 to the n, which is geometric. Burp, burp. Geometric, very easy to work with. You look at the common ratio right here, and our common ratio is equal to 1/3. Its absolute value is less than 1. This is a convergent geometric series. All right, what does all this mean? I took the absolute value of the terms. I got a convergent series. That means that the original series has to converge. And the reason why is because in absolute value, this series, this one right here, has to be bigger. This thing has to be bigger than the one where we're taking away some of the stuff. And we're smaller than a convergent series, therefore it must converge. So I write something like, since the sum of the absolute value, negative 1 to the n times n plus 1 over 2 over 3n, converges, then our original one, the one without the absolute value, need a copy and paste feature, right? So you don't have to keep writing all this stuff down, also converges. Maybe I say something like must converge. That sounds better. Okay, it is convergent. It's absolutely convergent, actually. Must converge. Ooh, watch this. Absolutely. Yeah, that gets highlighted too. Okay, all right, so that brings us then to the end of this particular objective about absolute versus conditionally convergent series. For these absolutely convergent series, well, maybe you have terms in your sequence that are alternating between positive and negative, but not regularly so. You can take the absolute value of those terms and see if that new series is convergent. If it is, we call that series absolutely convergent, and that means that the original series must also converge. All right, in the second objective, we're going to look at a new test. It's a fantastic test. It's a powerful test. It's called the ratio test.